So this is a lot of text, but to say just a few things. So we've got this type of electron. That's really the most important type of electron. So we've been talking about where the electrons exist and, how far away they are from the nucleus. But what's the reason for really identifying how far they are away from the nucleus? There must be a reason for that. And it's because the valence electrons, the ones that are the farthest away from the nucleus, are what? What's it say? The electrons that are farthest away from the nucleus are what? Have most energy, which means that they help control the chemical reactivity of that given atom. So if I were writing this down, I would say, okay, VE, valence electrons, all right. So far from nucleus, farthest, farthest, farthest?
Not farthest.
Most far. That doesn't make any sense. All right, we're going to go back to this. Okay. So they're far from the nucleus, and they have the most energy, which means it gives the characteristic to the overall atom of its level of reactivity. So let's say it controls the atom's reactivity. All right, well, there's a little bit more information here that's talking about valence electrons and what can we do with them. So what's something that can be done with the valence electron? Just like any electron, say again. Right, so they can either be removed or gained, but what about the inner electrons? Can you touch those? No, so the inner electrons, which are going to be, where's that? The inner shell electrons have less energy than those on the outer subshell, so we're not touching those because they're not really the reactive ones. The valence electrons are the very, very reactive ones. So there's a method to the madness, though, which is what this section right here is saying. These valence electrons are lost and gained not just willy-nilly. They're lost and gained to meet what? Divided by what rule? Octet rule. So they're removed or gained to meet the octet rule. What's octet mean? 8. Okay, so that's getting up to 8 valence electrons or losing them in order to go back to the last octet they had. We'll elaborate what that means in a second. So the valence electrons are far from the nucleus. They have the most energy, which means that they control the reactivity of a particular atom. The reactivity is actually controlled by how many valence electrons you have, actually, but they can either remove or gain them to meet the octet rule. And the octet rule comes into play, like, for example, if I'm talking about the second energy level, comes into play when you do, like, 2s2, 2p6. So in this valence shell, in this electron energy level that's the farthest from the nucleus, I got 2s2, 2p6. How many electrons are here? 8. 2 plus 6 is 8. And so we're specifically referencing the electron configurations when we're writing these valence electrons down. But we just have to make sure when we write them, we're aware of the possibility of things being gained or lost. But we already knew that was a possibility because we knew ions could be formed when electrons were gained or lost. We knew that was a possibility, but now we're just looking at it from the perspective of the electron configurations like we were writing yesterday. So one note, well, I have a PR table down here to help you guys with this. The group number of an element is equivalent to the valence electrons it has. And that's a fact, right? You will know that, and the periodic table, it will always be in front of you. So if you have the periodic table and you can read it and get the little details that you need to from it, it's a piece of cake. So I'm just making sure you understand that's the case. So there's some other information here, like the hydrogen, helium, lithium, and beryllium have a weird, they're really small, so they're octets, not 8 actually. They're octets actually called a duet, it's 2. We'll talk about that more specifically when we apply that. But in all, where are the valence electrons? On the outside. What's so special about the valence electrons?
They control reactivity.
They control reactivity. Okay, so this is what these are the main points. So an atom can gain or lose electrons in order to meet what rule? octet rule, which comes from the combination of the two electrons in the s sublevel and how many electrons in the p sublevel? 6. And this could be anything. This could be 3s2, 3p6, or 5s2, 5p6. It doesn't matter what the energy level is. It depends on the electrons that are there. And then when we lose and gain electrons, we already knew it, but what was it called? Formation of an ion. And then if I'm just looking at the periodic table, how do I know the number of valence electrons? Same as the group number. All right, so that's what you should have gleaned from this. I'm videoing if you need more information from this. Transition metals, we'll get to that little section once we get there. So looking at this periodic table here, and you guys have your own periodic tables. If you want to pull them out, we can add on to that. I just want you to write on the top the valence electrons on the top of the groups, okay? So how many valence electrons should be here? 1, put VE to say valence electron. How many should be here? 2, that's the second group. 2 VE, 2 valence electrons. And let's talk about why that's the case. I'm just letting you guys catch up with me here. So if I were talking about potassium, and I went through its electron configuration, it would be, let's do sodium. What's sodium's electron configuration? Go for it. Start at the top. 1s2, 2s2. That gets us here. 2p6 gets us all the way over here to neon. And then 3s1. Okay. So here is sodium's electron configuration. And this is where I need you to pay close attention, write down the details that you need to, but listen really well. When I look at an electron configuration, I can tell where the valence shell is. The valence shell, or the valence electrons, are in the outside energy level, right? You just write that definition down. Which is the outside energy level? 1, 2, or 3? 3, okay? So then put a little circle or square around that. This is the valence energy, or valence electron shell, the third one. Not 1, not 2, but 3. How many electrons are in there? 1. Everybody here is going to end like that. It doesn't matter what energy level necessarily we're on. They're all going to end at blah, 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 S1, 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 S1. You see, because we're only halfway through the S block? That's why they all have one valence energy, or one valence electron. But when I go to the end of S block, what I always end in, not just 2, but S2, right? So, 2s2, 3s2, 4s2, 5s2, 6s2, I'm always ending in 2. So how can I write this now for magnesium? What would change with this green writing up here?
3s2.
It would be 3s2. Okay, so that's for magnesium, right? How many valence electrons does magnesium, along with everybody else in its column, have? 2. So the third energy level is still the valence shell. The very outside energy level is the shell. And then in that third energy level, we have 2 electrons. And that's why this works out. Everybody in group 1 has 1 valence electron. Everybody in group 2 has 2 valence electrons. Skip over here to 3. What you think? 3 valence electrons. Okay, so let's pick one. Let's do aluminum. And I'm just going across because I'm picking sodium and then magnesium. We're going to do aluminum now. How does this change? So 3s2 stays, right? 3s2 is there because of the magnesium, and then keep it going. 3p. We're just going to aluminum. 1. Okay. What's the valence shell here? 1, 2, or 3? 3. So the third energy level is still the valence shell. It's the very outside energy level. So put a square around the 3. Okay, in that third energy level, how many electrons are there? 3. 1, 2, 3. So this is ending with 3 valence electrons because we're in the third group, right? So the third group has 3 electrons in the outside shell. So then sequentially, carbon's group should have how many? 4 valence electrons. Nitrogen's group should have 5 valence electrons. Oxygen's 6 valence electrons, 7 valence electrons. And who always has octet? The noble gases. Okay, so the noble gases they are the perfect atoms. They have octet already. They don't have to lose or gain electrons if they already have the 8 that they want, because it makes them more stable to have the 8. So let's go ahead and expand this a little bit more. Let's write the electron configuration for fluorine. No, not for fluorine. For chlorine. Let's do chlorine. So how would I modify this? 3p what? 5. So 3s2 stays with us. And then I go all the way through 1, 2, 3, 4, 5. So 5 into the p block. So that's a 5. Okay? I still have my third energy level circled for you, but you can now see how many valence electrons are here. 2 plus 5 is 7. Just like everybody here in the 7th group, they will always end in P5. Doesn't matter what the number is, but it's P5. And that's going to give us, in the end, 7 valence electrons. Change that for argon. This would be a 6 on the end, right? How many valence electrons do I have in my third energy level? 8. Everybody here is going to end in S2P6. So the number in the front will change because we'll deal with different energy levels as we go down the periods. But S2 and P6 will add up to 8 octet. Okay, so we're going to talk about ions from here, and then also some of the F block stuff we didn't get to yesterday. Okay, so can I get a thumbs up that you understand that the valence electrons are the same as the group? Okay, what's so special about valence electrons? They determine the reactivity. And can they be lost or gained? Yes, but who will never ever lose or gain? The noble gases, because they are perfect in all ways, right? These are cool kids, everyone wants to be like them. They will gain and lose based on this. All right, so let's talk about ions a little bit more now, okay? So, I'll talk about that in a second. So first, before we write this ion electron configuration, let's just write it for magnesium first, okay? Partner next to you, get going. Yeah, like a couple seconds.
No, we're just trying to figure out the electron.
All right, guys, let's get going. What is it? What's magnesium?
1 and 2, 3 S3.
Okay, pause. Eyes back up here. Looking at magnesium, that's your straight up magnesium atomic electron configuration. What does this right here mean? Okay, it's a what's the name of a positive ion? Cation, pause, right? Okay, that's a cation, and it has done what? Lost 2 electrons. So this is what you're thinking to yourself. Okay, I've lost 2 electrons. Where would those electrons have come from? From its, you were saying it, valence shell, from its valence energy level. I'm not going to go inside of the atom and go, hey, I want the first energy level ones. They're really deep in the atom. So we're not going to take electrons from the inside. We're going to take it from the outside energy level. So if I were to draw this like I were in 7th grade, it would look like this, right? So there's 2 electrons, and then there's some more. There's like 8 or something right here, and then there's 2 more. These 2 are which up here?
3S2.
Those are the 3s2 electrons. That's the third energy level s orbital. It's a sphere, but you know most things are. And those are the 2 electrons. So this is straight up magnesium. How would this change if it were our magnesium ion? Those would be gone, right? 1s2, 2s2, 2p6. And so I'm scratching those out, right? I've lost those 2 electrons. Who do I look like? Or is it a neon? Neon, right? Yes. Okay, so I am not neon. I look like the electron configuration of neon. Why am I not neon? Because I'm magnesium, but what makes me magnesium? Do I have 12? Okay, guys, just I can't see very well. Okay, so I have 12 protons still. I never changed protons, right? Nobody checks protons. So inside of this, we still have 12 protons, approximately 12, not 24, 12, 24 is the mass, but I was doing the math here, 12 neutrons, and now I have what? 10 electrons. It's the same stuff we were doing, right? It's just representing the electrons in a little bit fancier way. All right, so this right here is the it's the electron configuration for magnesium 2+ ion, but it looks like the electron configuration of a noble gas, and why would we have dropped off 2? What makes it perfect now?
It's balance.
Okay, it has what?
The octet.
It has octet. It has 8 valence electrons now, because who's the valence shell now? 1 or 2? 1 or 2? 2. So this is second energy level, and this is second energy level. So if I circled my valence electrons now, it would be 8. And that's the reason. There's a method to the madness. They don't just say, like, I think I'll lose 1. There's a reason, and it's because they want to back up to octet or go forward to octet. I saw some hands. Grant.
So let's say we get the 1s2, 2s2, 2p6, like as a question.
Mm-hmm.
It says like name the corresponding like element.
I would allow flexibility, of course, but I would name that neon, not knowing. If it says name the corresponding atom, I would go neon. If it said name an ion that this could represent, it could be like a ton of them, and I would have to be flexible.
Okay.
I'll be more specific, no worries, okay? All right, can I go to the next example similar to this? Okay, let's do nitrogen. Let's just do straight up nitrogen first, okay? Write the electron configuration. Straight nitrogen. All right, I'm ready. Start me off. Okay, pause. So back with me. 2b3. So we got 1s2, 2s2, 2b3. If I were looking at this right now, where would my valence shell be? First or second? Second energy level, right? So here's my second energy level right here. How many valence electrons are in my second energy level?
5.
2 plus 3 is 5 valence electrons. Now here's the predicament. And atoms, they already know this, but we don't. You can be split up 4, right? So 4 is in the middle of 0 and 8. So if you're on this side of 4, meaning you have 5 valence electrons, 6 or 7, you're not backing that bus up to go backwards. You're going to go forward. So I have 5 valence electrons. So is it easier for me to gain 3 electrons or lose 5 electrons? Yeah, that's a shorter route, right? We don't want to go the long route. It's not a scenic thing we're doing here. We want to get to business. So it's going to gain 3 electrons. Now, where does it have space to gain those 3 electrons? In its valence shell, right? But what type of orbitals? The p orbitals, right? Okay, so before I move on from this example to show you the 3 negative charge, why that comes in, can we just verify we know how to write orbital diagrams? How do I draw an orbital diagram?
1s, line over.
So line, 1s, this is labels. Up, down, okay. Uh-huh. Okay, hold on, pause here. Don't say it yet. When I say go, tell me whose rule we're following. Go. Okay, Hun's rule. So how do I fill this in? Up. Okay. Whoa, hold up. I only got 3. Okay, so from here, I've gotten nitrogen taken care of. But what we have space for are how many more electrons?
3.
3. Hence why nitrogen gets this 3 negative charge, because it has gained 3 electrons. And then we don't have to guess where they go. There's only one option here. Where do they have to go? Down, down, down. So what I might have you do is, like on a test, I could say, okay, write the electron configuration for nitrogen, draw the orbital diagram, and I could say, tell me where nitrogen could gain or lose electrons. And you would not tell me they'd lose any, because 5 is way too many to lose. 4 is the breaking point, because that's the middle between 0 and 8. So we'd gain 3 more, and I could tell you to circle them. Like, where did you add them? And you could circle them, because of course you probably don't have like a million colors to work with on a test. And then once you circle them, you would say this is the electron configuration for nitrogen 3 minus, but who does it look like? It looks like, say again, look where nitrogen is, bounce up 3 places. It looks like electron configuration of neon, not because it's neon, right? It's still who? It's still nitrogen because we never changed its number of what? Protons, that's the identity maker. But we've changed its charge, and it looks like a noble gas. Every single time you form a charge, the electron configuration will look like a noble gas because those are the cool kids. Those are the stable ones. They have octet. It'll happen every single time. Yeah. Mm-hmm. It's a half. It's actually half. I won't give you anything like that. That's more AP. The top half of the group. Hold on. They're small, so they may. I have to think about this. They lose electrons. No, they gain electrons. The top half of the group, and then the bottom half. What did I just say? Okay, half and half. It's based on the size of the atoms. We're not going to go that far. Yeah.
So they can technically bond with something like somebody in the same group.
For sure. Okay, let me go back to my picture real fast. So this picture that you guys just kind of annotated, tell me now, based on the valence electrons they have, knowing if they're going to form an ion, they're going to have 8 valence electrons at the end. Tell me the charges they would form. So everybody here has 1 valence electron. Is it going to gain 7? Lose 1. So what's its charge?
Positive.
Plus 1. Okay. Everybody here has 2 valence electrons. Is it going to gain 6? No, it's going to lose 2. And basically, it's like calcium has 2 valence electrons, right? It bounces back 1 to potassium, and it bounces back all the way over here to argon. That's what I mean by losing 2. It bounces back to look like the electron configuration of argon. So everybody here has a 2 plus charge. Okay? Everybody here has a plus 3 charge because it's going to lose 3 electrons versus gaining 5. Okay? 4 plus or minus 4. Don't mess with that one, okay? How about the fifth group here? Okay, so I heard some different responses. Raise your hand. What you got? Because it's going to do what? It's easier to gain 3 to get to noble gases versus to lose 5. Okay, we're going to shorter route. Everybody in this group?
-2.
-2, everybody in this group? -1, everybody in this group?
Perfect.
Perfect. Don't charge them, right? They're not going to be any gaining or losing of electrons. Yeah.
The thing we just did,
With the orbital diagram?
yeah, like the slide that we just were on.
Uh-huh.
How would you write the electron configuration? Like,
Or
yeah, we wrote the orbital diagram, but we did write the electron configuration.
so the nitrogen 3 minus,
Would you just?
you just add the 3 right there. So it'd be 1s2, 2s2, 2p6. But I did this on purpose, okay? This is what Grant was saying. This one looks just like that one, right? Then that's why I would never ask you the opposite. I'd just start you off with this and then you move forward. I'm not here to get you. I'm here to help you. All right, so these are the 2, like we did a cation and we did an anion. So for the copper and like things that are transition metals, I'm going to show you an example of that so you're very comfortable with that as well. Write out the electron configuration for straight up copper. Go. Straight copper. Not copper 2+, but copper.
29. Oh, also, I was trying to figure out how to write the electron configuration.
What?
No, like.
Oh, F block. Yeah. I'm going to do one more in a
confused
second.
on-
All right, Evan, what'd you get?
1s2,
Mm-hmm.
2s2, 2p6,
Mm-hmm.
3s2, 3p6, 4s2, 3p9.
Awesome. Okay, give me a thumbs up if you made that far. You remember when you hit D block, you do 1 subtracted from the original electron energy level. Okay, so if you have to look here, tell me, what is the valence shell? What's the energy level that the valence electrons are in?
3D.
4. You see the fourth one is the highest number, right? We see 1, 2, and 3, and then you see 4, but then the 3 tricks you because it's at the end. But you're looking for the 4th energy level because it's the highest, it's the outside shell. So put a little square around there and put valence shell just so you understand that the transition metals are tricky. You got to be a little bit more cognizant of what's going on there. Now, how many valence electrons does it have? 2. Okay, is that even close to 8? No. So it's got 2 valence electrons. So it's going to do what? It did to form an ion. And I'm saying this because sometimes they're just atoms and we just write it like it is. And sometimes they're ions, which means we change the electrons. So you said lose 2 electrons. So rewrite this or just note it. What's going to happen here?
Get rid of them.
We just get rid of them. Okay? Those are the 2 that would get lost if we were to form what ion? No, what ion? 2 plus. This is copper 2 plus. What I've drawn in, I haven't actually written it out. Copper 2 plus is 1s2, 2s2, 2p6, 3s2. And
How do you draw that?
hold on, 3p6. Okay, so I basically rewrote it without the 4s, which means it's lost its 2 valence, and it's copper 2 plus. It's still copper, right? It doesn't even look like a noble gas. Oh no, I'm sorry, I forgot the 3D. Is that what you guys are calling it? I'm sorry. All right, so this one doesn't exactly look like a noble gas, but what you'll notice is that in its 3rd energy level, it has collectively the 3s2 and the S2 and P6. That is where it's octet. But the transition metals are a little harder, and that's why I don't ask them too frequently. Questions there?
How do you draw that?
How do you draw? You're going to do the same thing, like line, just all these filled up. Same thing with your lines, and you'll have 5 orbitals for the final, right? But 9 electrons in them, so it'd be 1, 1, 1, 1, 1, 9. And you'd stop. That would be your end point with your 3D. Okay? Somebody asked me for F. Before I do F, okay? I know that you guys had some practice. You guys had some really long electron configurations. And I've told some people that I would tell you the shortcut. You ready? You ready? Okay. I promise the computer, it doesn't want me to shoot the shortcut, guys. Oh, okay, here we go. We're going to do this. I'm going to write on the board if I can't get the computer to work. Okay. And here we go. Okay. The noble gas shortcut. Now that you know the noble gases are the perfect electron configurations with the valence shell to be 8, what you do is you take what you would have written all the way to the noble gas, the last noble gas you passed, what you would have written, and instead of writing all that junk, we write the noble gas in brackets, like this. That argon in brackets means 1s2, 2s2, 2p6, 3s2, 3p6, argon, okay? And then you finish the tail end past your last noble gas you passed. This is called the shortcut. Now, when I say you can do a shortcut, by all means you're going to do it. But if I just say longhand, it means what we did yesterday. I will give you options, miss. Okay? So let's write. I want to show you an example of this. Okay? So the one we just did. Let's do copper. I'm going to go back to the copper one. Quick question. Ready?
All right, so let's say you ask us to do the arrows. Can we do the shortcut on that?
I would give you the option most likely,
Sweet.
only because I know your little fingers hurt. But let's do the noble gas shortcut for. Let's do it for lead. Let's do that instead. Okay, lead was the long one. You guys done your homework. So what you're gonna do, and I need to keep grabbing. I'm gonna go grab a PR
Does
table.
F go in there?
I'm gonna show you how that works.
Because I looked it up on Wikipedia and it had the shortcut version. And I was so confused.
Okay, just hold up. All right, so let's do lead. Now you would have written 1s2, 2s2, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 5. I'm almost done. This is a time of myself. 5d10, right? Is that 5? Yeah. No, 4d10, 5p6. Okay, 6s2, right? That's what you would have done. You would have made it that far, and then you're like, oh crap, what do I do with F? So this is where the F block, do you see the numbers change from 57 to 72? Doesn't make any sense, right? So this F block actually fits in right here. It goes in right there. So what does that mean? That means that if you were to write the electron configuration for lead and you were doing longhand, you would have made it all the way through here and you would have put 6s2, correct?
Yeah.
So that's this far. Then you would stop and put in what's this. That line right there means to insert cerium in friends, which is going to be F block. But like we did in D block, you did N-1, and F block, you do N-2. So instead of being 6, it's going to be 4. F, how many across? 14. And then once you get past the 14, you go back up here to where you were. And this is what? 5. Go all the way through, and that's what? What's
D10.
That's going to be D10. We're stopping here at D. So 5D10. And then pick back up where we were.
6P2.
6P2. So now there's a bunch of stuff in the beginning of this, right?
Yeah.
There's a bunch of la 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 la. 6s2 is us starting here. We inserted F block as 4F14. We went back and finished D block as 5D10. And we finished off the little bit of P block we needed, which was only 2N. Okay, now that's the really long version of that. So what do I do if I'm backing up to the last noble gas? This is lead, right? Who's the last noble gas it passed? Xenon? Yeah, because you back up to the last noble gas you passed, which is xenon. Okay, so I've done this on purpose because I wanted to show you how this looks. All that la 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 stuff I told you until we get to xenon, we can say that with brackets. We can say that by doing this. That's it. So you write xenon like that. That means blah, 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 till you get to xenon. And then because that is the last noble gas we passed, we do have to finish off with the S, the F, the D, and then the P. And that's it. That's the electron. That is the shortest I can make lead. Right there. Okay. I'm going to move on from this. We're going to go to our lab. I'll answer more questions with electron configurations probably at the end of class. This lab's a really fast lab, okay? I'm not having you get your own paper. I got out the data table for you because my little perfectionists like to use their data tables like a piece of art. But tell me 3 ways we can excite electrons. Go. No, how do we excite electrons? Heat, electricity, and high-powered light, like UV light, okay? So that's what we're doing. But we're not going to do all 3 of those. We're just doing 1 for now, okay? So this is your reminder. Heat, fire, and electricity. Which one are we doing today?
Fire.
Fire, okay. Reminder, electrons jump from the ground state to the excited state, and when they fall back down, they produce light, if it's in the light spectrum, okay? I'll talk about this example whenever I get done. But here we go. Let me demonstrate for you what we're going to do. That's not this. Pass back some of those. Pass back some of these. Let me grab you some more of those. Here's some more of those. And then the copier ate my lab sheet, so this, if you don't get one, I'm going to give you this one, okay? You have extras? Pass them this way. Annabelle, pass them this way. Thank you. All right, so you have to watch and learn. I will show you, after I get your full attention back, I'll show you how to do this, and it shouldn't take us more than 30 minutes. Basically what we're going to do is we're going to stick a little metal loop in the fire, and we're going to say, ooh, ah, and then we're going to write down the color we saw. It's super, super simple, but I'm not even having to pull up the lab notebooks because it's literally that. So the data table side of things is for you to record your results. Now we're going to do that for all these nodes. A lot of you guys will notice that some of the ones I passed out. Do you notice I made a typo that says copper? You see the CuCl? You guys have any? You see the CuCl? It's the
Yes.
third down. Instead of writing copper, do you see what I put underneath there? Barium, yeah. Not barium. It's definitely copper. So scratch that out for me and change barium's name to copper. Okay. So on the on the left-hand side of the data table, you see the known solutions like lithium, potassium, copper, sodium, strontium, calcium. So you see all this there. On the other side, it says unknown. So after you get the color scheme of the colors produced by these solutions, I'm going to give you some unknown solutions, and you can match them with your knowns and figure out if they are based on the colors. So, the only other thing I'm going to tell you to do is if you contaminate my solutions, I will haunt you in your dreams. So you have to put the loops, the wired loops, back in their home container, back in their original container, okay? Now, I forgot my shoes today, so I'm going to like show you guys some things and then leave you. If you don't have your shoes on, you need to get your shoes on. You know what? Groups of 3, bye. Groups 3, go. We'll get started. Groups of 3, get your goggles on. You guys have 10 seconds to make a choice. Let's go. 10 seconds. There's extra trees back there.
I feel like Anna just got out.
Oh, yeah. Get that box rid of Alright, you have 10 seconds to stop your bodies from moving. 10, 9, if you don't walk, you gotta get them. 7, 6, 5, 4, 3, whoa, do not start striking the arm. Okay? Don't even start striking. You're ready. Give me another one. You guys are sharing. Not Alright, I'm going to remind you, 5, 4, 3, 2, 1, listen. Look at the butt. Look at the butt. Righty tighty all the way. The gas inlet valve is what we want tight because we don't want a flamethrower, we just want a little flame. So once you turn it, hush. Once you turn it right, you're going to go half turn to the left to open it enough. Maybe a little bit more than a half turn, just a hair. And then now you're going to turn it back up. Look down the barrel. I see some people with no goggles on, so come on. Okay, so you're looking down the barrel now. Looking at the barrel, righty tighty, turn it righty tighty, get it all the way there. And then, so righty tighty means turn to the right. And then you're going to take a left turn, 4 full turns. Okay, 4 full turns. And that should give you enough oxygen to get this thing lit. And then you have your person who's your striker. And the person who's your striker is going to be the 3, 2, 1 and tell you when to go, okay? I want you to turn it on now. If you can't get it lit, then stop, okay? See, alright, stop. Stop. The gas system goes out. Stop. That means stop, like no striking. Turn your gas off for a second. I will reset it. Got it? Thank you. Alright guys, look, and stop trying now, stop trying. If you don't have it lit yet, you'll get there shortly, okay? Watch over here so that you guys can see. I don't see all your eyes yet, okay? I'm gonna wait on you. I said stop trying. Thank you. So here's what you need. You need an inner blue cone, and that inner blue cone, okay. Jesus, like, can somebody turn that dude on? That's a single one.
Why is it so cool?
Okay. The middle, no, the single one. The single one? The single, yes, okay. So, everybody has a bucket.
Okay.
Guys, I know some of you are still working. Watch, okay? You have a bucket. Everything has a tape piece to the nitrile wire loop, or it has a rubber band. And we want to make sure that it's always going back, because if you can make these out conjuring your dreams, right? All you do is it's really simple. You unscrew your lid, and this is copper. You dip the loop, and you just get a little tiny bit. It's just going to hang out in the middle of that little loop on the end of the nitrile wire metal piece, and you put it in the inner loop cone on the side of the inner loop cone.
Oh my god, that is so cool.
Yeah? Oh, you didn't see it? Well, hold on. See, I just got to do it again, right? You stick it right back in there, and you just go, oh. Okay, so make your observations, and you're done. You don't want to brand anybody with this hot tool. You close it back up, and you move on to the next
Alright, you're gonna be quiet for me in 3, 2, 1. Continue to be quiet. So a lot of you guys are already moving across getting all your solutions done. There's other solutions in buckets near you. So if you don't get all the colors filled out for your data table, there's going to be a solution that's the one you need at a table near you. Don't run around with solutions, okay? Walk over there and ask them if you can use that and put it back where it came from. In about 5 minutes, I'm giving you the unknowns. Get all of the data table ones filled out. No, SR.
Relax, bro.
Who has lithium? Li, lithium. Yeah. You guys can use Alright guys, listen in 3, 2, 1, listen. Some of you guys are already done with the first data table. Here are where one person for your group needs to be listening. Here are where all these unknowns are. You must get 3 of them correct, meaning you're matching your colors. If you saw some color in the beginning, you know that identity, you see it again, you're thinking it's probably the same solution, right? These are unknowns, but they're the same ones you've been testing. So I've got like 12 of them over here. If you want to take 2 at a time and then pass me your table, bring them back, leaving them here is what we need to do. Or you can come grab what they need to start identifying unknowns. Grab 2 at a time. Watch my table over here because people don't have them because you got a bunch of stations. You have one more minute with the unknown. That's it. One more minute.
Yeah, no, I just didn't.
Alright, I'm turning gas off in 10 seconds. Yeah, you guys Yes, okay. Okay, guys. 3, 2, 1, stop. You Usually when I say stop, it's for safety reasons. Okay, so gas is off now, right? Hey, don't touch your Bunsen burners because they've been on, right? So don't try to rip it off yet because they're hot. Common sense. Now, do your analysis questions with your lab station. Go. Just to note to self, I know you're working, listen. Question 3, where it says, listen, explain how the colors observed in the flame test are produced. Don't say, if I stick in the wire in, use your chemistry background knowledge to tell me why that's occurring. Use your scientific vocabulary. So number 3 is going to be the hardest, the more chemistry one, and number 6.